So we went through all of the derivations in order to come up with this matrix form, and this actually makes it very easy to discuss the solution schemes. The main determining factor for the solution scheme is the time step level at which you evaluate the transmissibility matrix, the solution vector on the left hand side, the accumulation matrix D, and the source or sink matrix. And one of the most common schemes for very difficult problems where pressures and or saturation is changing a lot is the fully implicit scheme. Why? We use it because it is unconditionally stable. So very close to your wells, where the pressures will be changing a lot, where the saturations will be changing a lot, it's common to use fully implicit scheme. And it only means that all these question marks here are evaluated at the current time step n+1. And so you see you have n+1 everywhere you add question marks. These terms do not change. Your time level do not change because those came directly from the discretization of the storage term on the right hand side, which was originally ddt of phi rho s. So those don't change. They came from the backward finite difference approximation to the first order. So how do we move on from here? Move all the terms to the left hand side, you obtain what is called the residual. So take this term to the to the right hand side. Actually, whichever way you do it is not important. But for convention, here I'm taking it to the left hand side. So it's minus this term minus the Q term. And now we can use Newton-Raphson scheme as I explained previously in module 3, when I gave you the Taylor series expansion and went ahead to explain that you can do Taylor series expansion also on vectors instead of just on scalars. And when you do that, you will obtain what is shown here, the Jacobian matrix multiplied by the change in the solution vector equals minus the residual. And this you can solve by pre-multiplying. So this is essentially Jacobian times delta x equals minus r, because this is Jacobian, and pre-multiply by inverse of Jacobian. This becomes an identity matrix. Do the same thing here. And in MATLAB, it's basically just minus Jacobian backslash r, and you get this change in the primary variable. And what do you do with that change in primary variable? You can add that to whatever the previous value was. So starting out the simulation, you will be given initial conditions. So that will be initial pressures and initial saturations everywhere in the domain. And then you begin to increase the time step, and within each time step you change the iteration level. And I summarize that in the slides I added at the back end of your slides. Which is here. So we can actually discuss what's in here. In the fully implicit scheme, we don't make any simplifying assumptions like we will begin to make in the other schemes. We use the generalized Newton-Raphson's method to find the roots of the equation, which is what I'm going to explain on the next slide. Of course, you already saw the Jacobian matrix, which is the derivative of the residual with respect to all of the primary variables in all of the grid blocks. The primary variables are the unknowns. This is the main reason why we use it. It's unconditionally stable. And that means you can use any time step size. And that's good typically when you're running long simulations, right? You don't want to be restricted to use very small time steps, because when you use very small time steps, then you will need to run the simulation for several time steps to get to the end of the simulation. And also, it rarely gets stuck for difficult problems, like I explained, where pressures or saturations are changing a lot. And in IMEX, we can specify the convergence criteria, which we get to do in the labs. So this is really where I'm getting at. For the fully implicit scheme, I've just given you this equation right here. But here I show you again how we derive it from Taylor series expansion. So this is your residual, and you can express it this way. This is your Taylor series expansion, but for a vector x instead of a scalar small x like we did before. And that is why the derivative of the residual, which is a vector, with respect to another vector x, gives you a Jacobian matrix. This is your change in the primary variable, and obviously this is your residual at the current time step, but at the previous iteration level. This one is current time step, but current Newton-Raphson iteration. And this is a typo. It really is. It should be minus Jacobian / the residual, the matrix before the vector. That's how we evaluate it in MATLAB. So the Newton-Raphson scheme actually linearizes a system of nonlinear equations. Very important. Those two equations that I showed you for the oil and for the water, they are actually nonlinear. The Newton-Raphson scheme linearizes it, and then you're able to evaluate delta x, the change in x, at every Newton-Raphson iteration level. But what we are looking for is actually x at n+1. Here I'm using k+1, same deal, representing the time step. And at i+1, representing the iteration level. This is what we're looking for. But we're solving for delta x. So how do we get x from delta x? I already explained that before. At the current iteration level, current time step, it's the value at the current time step, previous iteration level, plus this delta x, which we just found. And so this is obviously a nested loop, right? This is time stepping, this is Newton-Raphson iteration. So Newton-Raphson iteration is inside the time stepping iteration, which I will be showing on the next slide. But before that, even though we use x's, we realize that x's basically correspond to PO and SW. So for PO, this is what it is. For water saturation, this is what it is. Same thing, right? And now, to further clarify how it is implemented in code, this is your time step loop. So within a time step loop that goes from 1 to the last time step, say NT, we have another loop that goes from NRI 1 to maximum NRI. So this one is T going from 1 to NT. This is NRI going from 1 to maximum NRI, and typically this converges in less than 8 iterations. So we like to use anywhere between 8 and 12 as the maximum NRI. And first thing is to solve delta x, like we already wrote before, minus Jacobian / R and then check, is delta x still changing a lot? If it isn't changing a lot anymore, you have converged, you exit. You obviously update x before you exit the loop. If it's still changing a lot, meaning you haven't met the tolerance, which more precisely means the mass balance error is still greater than the tolerance. So what you really want to do is to make sure that the error, the residual, is less than the tolerance. Whenever it's less than the tolerance, then you've converged, update x, and then step out of the loop and go to the next time step. If it does not converge, you stay within this loop and you keep doing this until the residual meets the tolerance. When it meets the tolerance, you're done with that time step. You have the solution for that time step. You move up forward one time step. So that's how the Newton-Raphson's method or iteration works.